We'll continue our discussion on semiconductor diode lasers. So let's first look at some typical laser structures. Basically, how the devices are constructed. So the simplest type that one can have is what is known as the stripe geometry. So basically, you start with N plus group indium phosphide. Then you have the N layer, and then you have the active region. So this is depending on the wavelength of your operation, of course, right? The mole fractions. And then on top you have the p-dop layer. Okay, and so basically you have a metal contact here, and current is sent like this, and then a metal contact on the bottom where the current comes out. Okay, so basically the carriers are flowing like this. There is recombination happening here in the active region, and so the device length is along into the board, right? So the mode coming out has elliptical shape like that, right? And that's how the mode is coming. So typically, like for this stripe geometry, if you look at the mode size, right, that's about 1/5 micron. So like 1 micron in the vertical region, vertical direction, and then about 5 microns in the horizontal direction. That's typically the mode size coming. So you can see it's highly elliptical, right? So it needs to be converted using some cylindrical optics into a circular mode before we can couple well into a fiber. Okay. And typically the threshold currents beyond which you start getting lasing for these structures is typically like 50 to 100 milliamps. Okay. So you can make the device a little bit more efficient by sort of etching this P region a little bit down further, right? So to confine the mode a little bit in the horizontal direction, right? Here basically because there is no confinement in the horizontal direction, that's why sort of the mode is highly elongated along the horizontal direction. So if you go to what is known as a ridge geometry, right? So there basically so you have metal contact here, and then you etch. So this is some dielectric here, let's say silica. You have P plus, and then a P region here, and then your active layer. Okay, and then sort of the N in this. Okay, and then metal contact at the bottom. So basically, by etching into this P region here, basically what you do is you get some horizontal confinement, right? So basically, the mode sort of looks like that because you're getting some confinement in the horizontal direction here, right? So it's a little bit more circular compared to the stripe geometry. Okay. So for example, the coupling into fiber becomes a little bit more efficient. Okay. One can do even better by going to what is known as a buried heterostructure geometry. Okay, so where we basically etch into the active region as well. Okay, so basically we etch into the active region, and basically the active region only extends to a certain small width, not to the entire width of the device. So it looks something like this. Okay, so yeah, so basically you etch into the active region. So you can see now the active region is basically the small region here, not extending to the whole width of the device. So basically now, of course, the light is only generated in the active region, and also you're getting lateral confinement here. Like in the vertical direction, you're also getting lateral confinement in the horizontal direction. Okay, so the mode becomes close to circular, so the ellipticity becomes less than 2. So typically, like sort of the mode sizes here, you can get uh, in both directions is sort of like, let's say, about couple microns. Okay. So of course you can see that. So this is most complicated to make, right? You have a lot of different layers and a lot of etchings going on in the middle. Like this is the simplest to make. You just grow different materials on top of each other. The next more complicated one is this, and the most complicated one is this. But this gives you the best performance, right? Also, all the carriers are injected into this very small active region compared to like here, for example, right? So the threshold currents for this is the lowest, right? And also the mode comes out almost nice and circular, so that you can couple well into a cine-mode fiber. Okay, so with this kind of bind heterostructure device, typically the coupling efficiency into fiber can be like 50%. Okay. With these kinds of modes, it's difficult to get maybe 10-20%, but with this you can go 50% or more. Okay, and then finally there is also another type of structure which is known as a big cell. So this stands for vertical cavity surface emission laser. Okay, so as the name suggests, so in all these three structures, right, the cavity is sort of in the horizontal direction, right? So along the length of the device. Like the current is injected in the vertical direction, but the cavity is in the perpendicular direction, the horizontal direction, right, into the board in this case. So here what's done is, instead of making the cavity along the length of the device, we actually make it along the height of the device itself. Okay, so we will see how that's done. So basically, you sort of form mirrors here, and the cavity is formed in the vertical direction, height itself. Okay, so typically this height is much smaller than the length, right? So we saw like the width is typically maybe 10-20 microns, and the length is like 100-200 microns, right? And that length is basically giving you this FSR or the mode spacing, right? So for a cavity length of like 200 microns, you typically get a mode spacing of a nanometer around in the infrared range, or like a couple hundred gigahertz, right? And we saw that like if we don't play some tricks, basically if you just take this device and operate it, we'll get what is a multi-mode output with many different frequencies, right? So one way to actually make your laser single mode, so we discussed a couple of methods last time. Another way to actually make it single mode is to make the cavity very small, right? Because as we saw, the FSR scales inversely with the cavity length. So if you make the cavity length very small, such that the mode spacing becomes greater than your gain bandwidth, right? So basically, only one mode, one longitudinal mode lies inside your gain bandwidth, and the next one is outside. So by definition, then you have only one mode to lace, right? And then that way you ensure that. So that's how. Yeah. So there is a question if there is a cylindrical shaped active region. So basically, I guess what you're saying is if this somehow can be made circular, and then going into the device along the length, of course, so it looks the active region looks cylindrical. Then the mode, yeah, would be circular, right? But remember how these structures are made is, so you're starting with the substrate and you're growing consecutive layers on top of each other, right? So it's like I mean, you can see automatically that you'll get planar structures, right? And it will be difficult to make. So by etching, you can see I can make like some rectangular kind of structure, but to make it circular is quite difficult. So yeah, so basically this big cell. So we make a window on top for the mode to come out. Okay, so we have metal contacts here and here. Right, so basically your current can come in through these. And then there's a window here for the mode to come out. Okay, and then what you do is basically, so on top of your substrate, it's an indium phosphide, right? What you first do is you grow multiple thin layers of alternating materials, right? High index, low index, high index, low index. So you grow multiple layers here, which act as a DBR mirror. So, right, you alternate between some different material compositions here, and you get this Bragg grating of high and low indices. Okay. So typically these layers are very thin, like maybe 10 nanometers, repeating many times, like 10, 20 times. Right, and then you have your sort of N region, and then active region, and then P region. So, and then you could also etch the active region. So you could have like some dielectric on the sides here, such that your active region is very is small compared to the total width of the device, right? And so basically now the current, since it's dielectric here, has to flow through this narrow active region where the recombination takes place, right? And then finally, what you do also, you grow a DBR mirror here on the top. Okay, so now basically you can see that, so you form a cavity, so you have mirrors here and here, and you form cavity in the vertical region. Okay, so basically you have some mode of this cavity. Okay, so you generate light here, and then it goes back and forth between this cavity, and eventually light is emitted out in the vertical direction. Okay, so the effective length of this cavity here, right? This length L can be much smaller than, so in these cases, the typical length we saw was like 100, 200 microns at least. Here you can see that it's much smaller, right? Each of these layers are probably hundreds of nanometers. So the total length for these VCSELs, one can have as short as a micron up to, let's say, 10 micron. Okay, those are the typical length scales of this vertical cavity here. Okay, so then if you try to calculate the FSR, which is C over 2 refractor index times length, right? So again, refractor index is typically like 3.4. Okay, so this now comes out to be greater than like a terahertz. Okay, so and which is typically greater than the gain bandwidth. So recall that we had curves like this, right? So if we plot the gain versus sort of frequency, we saw we had curves like this for different carrier concentrations, right? And so there was a range over which of frequencies over which you get the gain. But basically now what you've done is made FSR. So if there is one mode here, the next mode is outside the gain bandwidth. Okay, so basically by definition only one mode experiences gain, so only that mode can exist. So you have a single mode, single amplitude laser, right? And not only that, because now the active region is so small here, typical threshold currents here we can bring it down to like a milliamp or so. Okay, you can see much smaller, almost 2 orders of magnitude smaller than the typical diode laser structures. So for these VCSELs, yeah, you can bring them down. So operate them at very low currents or low DC powers, basically, right? And these can also give you very high modulation bandwidths. So we'll discuss the laser characteristics, and so basically if you modulate the current here at some frequency, of course the light output also gets modulated, and there is a limit to how fast you can go. And with these VCSELs you can go to gigahertz frequencies very easily. The only limitation with these VCSELs is basically the power coming out, optical power. That's limited to like typically maybe 10 milliwatts is the maximum you can get in these VCSELs. Okay. So that again is basically because your volume of the active region and the volume of the cavity is so small that basically the number of carriers decombining and the number of photons being generated is small. So with these sort of conventional devices, you can get maybe up to 100 milliwatts easily, but with VCSELs you're limited to less than 10 milliwatts. Okay, so yeah, now basically we'll discuss sort of the main operating principle of these semiconductor lasers and sort of how they are constructed for some for sort of the most widely used types of lasers. So now let's try to see basically. So for LEDs also we derive this sort of Li curve, right? So for a given input current, how much optical power do I get out, right? So similarly, if we want to do for the laser, right? So one difference we'll see is that so the laser characteristics will be nonlinear, right? For the LED, we saw that it was just a straight line relationship. So the power coming out was directly proportional to the current. But here we'll see that the characteristics will be nonlinear, and specifically we sort of discussed qualitatively already, right? So there will be a current up to which, right, we are sort of below the population inversion and where the gain is below the loss, right? So that is below threshold. So there you can imagine the output will be quite small. It will be almost like it's an LED, right? And only the spontaneous emission events are giving you photons. But once we cross this threshold, right, when once gain overcomes loss, then we will suddenly get a very bright output, right? Because now stimulated emission will take. Okay? So let's see mathematically how we can model this. So these lasers are typically like grown on a small chip, right? And then they can be packaged along with the optics, and then the fiber is what is known as pigtailed or directly attached to the device. So basically, what you get is like you get this package device, typically what is known as a butterfly package, right? And then the fiber is already attached to it, and basically the light comes out directly into my fiber. Okay, so basically we're interested in the power current characteristics. Okay, so for the LED, basically there was only one parameter on which the optical power emitted depended on was basically just the carrier concentration, right, in the active region. There was some rate of recombination, and so basically, depending on the number of carriers in the active region, you've got some rate of photons being generated, out of which a fraction came out, right? But here, because stimulated emission is happening, so there are two quantities which will sort of determine the characteristics. One is, of course, again the carrier concentration in the active region, so the number of electrons and holes, but also the number of photons in my laser cavity. Okay, because you saw that stimulated emission is basically the photons which are already existing stimulate the emission of more photons, right? So you can imagine if there are more photons present in the cavity, the rate at which they stimulate the emission of new photons will also be higher. Okay? So now basically both these factors will determine my finally output power, and they'll be coupled to each other. Right? So we'll have two rate equations. Okay. So one is for the carrier concentration. So N sub C is the carrier concentration, or the total number of carriers in the active region. Okay. So NC here is the total number of carriers or electron hole pairs in the active region. Okay, and so just like in the LED case, we can increase the carrier concentration by an injected current. Right? The carrier concentration goes down because of recombination, right? So this tau sub C is the net carrier lifetime. Right? So, right, so this was a combination of the radiative and non-radiative rates. Right? So for the LED, this was all we had. But now, so you can think of this as being just the spontaneous recombination rate. Okay? So, right? So just carriers spontaneously recombining and giving out photons in sort of random direction distributed over the 4 pi square angle. But now there is an additional term. Okay. I don't know if this is visible, so I'll make it switched. Okay, so this additional term is the stimulated emission. Okay, so not only are the carriers recombining due to just spontaneous emission, right, giving out photons, but they're also being stimulated down by existing photons in the cavity, right? So the spontaneous rate is this one, and then the stimulated rate depends on the number of photons in the cavity. So n sub ph is the total number of photons in the sort of laser cavity or the active region. More specifically in the active region. Okay, so basically the difference between the laser and the LED is this additional term here, which is basically, right, so this is spontaneous emission and this is stimulated emission. Okay, and also in addition, we also have a rate equation for the number of photons in the cavity. Okay, so in the LED case, we just said, okay, the number of photons is just proportional to the number of carriers. Right? But here we'll see that we have coupled equations, but because of this additional stimulated emission term, the relationship is not so straightforward. Okay, so for the photons, of course, so the stimulated emission event will generate a new photon, right? So I have an incoming photon, it stimulates this transition, so at the output now I have an additional photon, right? So this term will have a positive sign here for the photons, right? So the stimulated emission is reducing the number of carriers but increasing the number of photons. Then how else can the number of photons increase? Again, by this, if you have this spontaneous emission, right? So I have, so this is actually not entirely the spontaneous emission, right? Because this, remember, includes both the non-radiative and the radiative rate, right? So only a fraction of this is the radiative rate, which gives me the recombination, which gives me spontaneous emission. Right? So to be totally true, this is not like this is the spontaneous emission rate is proportional to this, but it's not equal to this because remember tau c has contributions from both non-radiative. Okay, so this is the spot. So again, this is stimulated emission. This is spontaneous emission. Both of which are increasing the number of photons. And then, is there a way for the photon number to decrease? Yes, of course there is a way, right? Because remember what is happening finally is that the light is coming out of the device, right? So photons are leaking out of my device. So that can be modeled as my cavity having some photon lifetime, tau sub ph. Okay, so a photon which is created in the laser cavity stays for roughly an average time of tau photon, so it bounces back and forth few times before it leaking out. Right. So the average time for which the photon stays in the cavity before leaking out is this tau photon. So this is known as the cavity lifetime, or the photon lifetime. Okay. So this proportionality constant G here, okay, that's something like the gain, which depends on this population inversion, right? How many carriers I have in the excited state. So this capital G here is related to this small g that we discussed last time, right? So the small g was, remember, basically how this was the gain coefficient, right? So the field here was, or the power in the cavity was experiencing gain like this, e to the gz, right? This small g, and this g was dependent on the carrier concentration. N is carrier. Oh, sorry. Yeah. So this is NC. You're right. Right. NC. Yeah. Right. So basically, we have two equations here. You can see for NC and N photons, which are coupled to each other. Yeah. So this is the gain coefficient. Remember. So this has units of per length, right? This capital gamma is, remember, because this is the confinement factor of the mode. So what fraction of the power is in the active region, right? So there is some mode profile here, and only a fraction of it is in the active region. So typically we said that this was about, let's say, 40% or so. Right? And then this Vg is the group velocity of the photons in the laser cavity. Okay, so group velocity, so velocity, is meter per second. So you can see that the units of G is per second. Right, which makes sense because here I have some dn by dt is equal to g times n. Similarly here, so the units of G are per second. Okay, so recall that this G depended on the carrier concentration, right? Something like this. So this went as this cross section times. So I use small n here for the concentration, right? So this was something like or in other words, so I'll divide by volume and then NC minus NT, right? So we saw that last time G was some cross section multiplied by my carrier concentration minus a transparency concentration, right? So I've divided by volume here so that this is now total number of carriers. So volume of active region. Okay, so you can see that basically this capital G I can write as some constant times the number of carriers in the active region minus some constant carrier number there. Right, so this N naught I mean, This N naught is just NT, right? So this is the number of carriers at transparency, right? When gain is 0. So this is the number of carriers in the active region that you need to just sort of be at the threshold of population inversion. So now you have equal number of carriers in the excited state and ground state. So that absorption is equal to emission and gain is 0. And then beyond that, you start getting gain. And so this Gn is a constant which depends on, you can see, confinement factor, group velocity, this cross section divided by active region volume. Okay. So Bg, so sigma g is a material property, right? So then volume of the active region basically depends on the device construction. Also confinement factors depends on that a little bit. Bg also is determined by your waveguide that is formed. So these depend on sort of the device, and sigma g depends on the material you use. So okay, so that's G here. So other things here. So tau C, we've seen this for LEDs. Typically tau C is in the few nanosecond range, like let's say 2 to 5 nanosecond in that range. Typical carrier lifetimes. Okay. So the spontaneous emission rate here, RSP, that we can write as this gain factor G again, multiplied by something which is known as the spontaneous emission factor. Okay, and this NSP is typically around 2. Okay, so this capital G we can see from here is basically proportional to the carrier concentration. Right? So this number is proportional to the carrier concentration, right? And the proportionality constant again depends on these factors here, right? What is this NSP? So it's sort of roughly like the number of spontaneous emitted photons in the cavity at any given moment of time. So you can obviously imagine that once we cross threshold, right, we'll create a lot of photons in the cavity. So this number of photons here will be a very large number, right? Of course, much bigger than 2. So this will be much smaller than this above threshold. Right. In other words, we are saying that the spontaneous emission rate will be much smaller than the stimulated emission rate, because the number of photons in the cavity will be much bigger than 2. Right. Once the device starts lasing. So typically, basically, what we are saying is this term typically will be much smaller than this term. Right. So to first order, typically what we can do is actually neglect this spontaneous emission rate. Okay. So it becomes important for certain other things that we'll see. But if you are primarily interested in sort of like the power current characteristics, typically this contribution is very small and can be neglected. compared to this two. Okay. So all the terms here are defined. Now the only term remaining here is this tau photon, the cavity or photon lifetime. Okay, so that depends on the losses in the cavity, right? So you can imagine if you have large losses, the photon will stay in the cavity for a very short time, right? So either get scattered away or get absorbed or leak from the cavity, right? So if you have large losses, then the lifetime will be small. So you can imagine that this quantity has to be proportional to the losses in the cavity. So basically, more precisely, this photon lifetime I can write as sort of inversely proportional to this loss rate of the cavity alpha, or loss coefficient of the cavity alpha subcavity. This is again the group velocity of the photon. So this alpha, again, units are per length, right? So per centimeter, let's say this is again so centimeter per second. So you can see this is units of second. Right. So what is this alpha cavity? That's the total sort of loss coefficient, attenuation coefficient of my laser cavity. Okay. And we saw that basically, so the loss has two contributions, right? One is sort of some internal loss here happening, which could be some absorption in defects or some scattering due to roughness or something, right? So that there is some internal loss coefficient. And then, of course, from the mirrors, right, at the edge of my device, these mirrors are not 100% reflecting, so the photons are actually coming out, so there's a loss there. So this has two contributions. So one is the internal loss coefficient, right? And then the other is the mirror. Right, which gives me my total cavity loss. And so, yeah, this is some internal loss coefficient depending on scattering losses and absorption losses due to defect, etc. This mirror loss, recall, was like this. So it depends on the mirror reflectivities R1 and R2 like that, log of 1 divided by 3. Right. So if my reflectivities are high, then this alpha mirror is small, and vice versa. And so recall, basically we had a threshold condition, right? Which was basically where this gain coefficient G became equal to the loss in the cavity, which was basically this internal loss plus mirror loss, right? So this is basically just also equal to the gain coefficient at threshold, right? So I can also just write this as along with the confinement factor, right? So here I've used this expression that we had last time, right? So at threshold, basically the gain at threshold times the confinement factor had to be equal to the total loss, which is the internal loss plus the mirror loss, right? So this we did at last time. So you can see that basically the photon lifetime is also inversely proportional to the gain at threshold. So again, like if your losses are high, the gain required to reach threshold is high, and the cavity lifetime is small. Okay, so typically we saw that so this threshold gain values are typically, let's say, in the 10 to 100 per centimeter range. Okay, Vg is C over the group index. Group index again typically 3.5 or so. So if you put the number and then this confinement factor, let's say about 40%, this tau photon typically is in the picosecond range. let's say 1 to 10 picoseconds somewhere there. So you can see that this photon lifetime is much smaller than the carrier lifetime. So carrier lifetime is nanoseconds, but photon lifetime is picoseconds. Okay, so 3 orders of magnitude lower. This is basically saying that the photons stay for a much shorter time in the active region compared to the carriers. So the photons are responding much faster, right? They are getting generated, then immediately emitted, whereas the carriers stay for much longer before being reconnected. So this effect, right, is what gives me higher modulation frequencies that I can achieve with lasers as compared to LEDs. Right? With LEDs, again, the only determining factor was the carrier concentration, which responds quite slowly, right, nanoseconds. But now in the laser, we have these two sort of dynamical quantities coupled to each other, and one of them is actually responding much faster. Okay, so we'll see that because of this, we can reach much higher modulation frequencies compared to LEDs. Okay, so basically, if you want to describe the laser operation, we can just use these two coupled equations and then look at it in different regions. Try to solve them in different regions of operation. Okay, so yeah, so first, so as I said, to first order, we can just neglect this term. So the equations become a little bit more simpler. Okay, so if you first want to look at the DC characteristics or CW, continuous wave operation, that means I have a DC current going into my laser and I want to see what power is coming out. So basically, since I don't have any time varying current, eventually things will reach steady state, right? So that the time variation of this carrier concentration and the photon number will reach 0. So right. Okay, so yeah, so each of these quantities now on the left hand side are 0 in steady state. So we can start from here. So we can immediately see, right? So the second equation here implies that if I take G minus 1 over tau photon times n photon is 0. Okay. So this quantity G, remember, is proportional to the number of carriers, which is sort of. So if you look at below threshold, so let's first look at low currents or below threshold. Basically, this G, so 1 over tau photon is a number, right? It's a constant. So tau photon dependent on my fundamental quantities of my laser cavity, right? So this is some constant here. This G depends on the current. So for low current, basically this G is less than 1 over tau photon. Okay. So anyway, the point is it's not equal. So this number is not 0, right? So the only way for this product to be 0 is basically if the number of photons is 0. Okay, so basically what we are saying is below threshold, there are no photons in the cavity, right? Which means that there is no power coming out, right? So this is telling you that up until, for low currents, up until we reach threshold, basically I'm not getting any output. Of course, this is an approximation, right? We neglected the spontaneous emission term, right? If we include that, basically we'll get what we got for the LED, right? We'll get a photon number which is proportional to the carrier concentration or the current. Okay, but anyway, that output will be very small compared to what we'll get above threshold. Okay, so for all practical purposes, we can to first order approximation say that there is no light output below threshold. Okay, there is some finite light output, but that value is very small, and since we've neglected the spontaneous emission, we are seeing this. Okay. So now if you look at this equation here, right, so now below threshold, so n photon, if you put 0, right, then this term goes away and you can see that we basically get the equation we had for the LED, right? Just the current injection and the carrier lifetime. And then if we say the carriers have also reached steady state, then you can see that the number of carriers is just given by the current, right? And now again, if we say there is a spontaneous emission rate which is NC divided by tau R, then that will give you the output of how many photons are coming out, right? Just like the LED. So, yeah, basically we can say that below threshold, the laser is operating like an LED, and the output power is very small compared to what we get above threshold. Okay, so yeah, basically below threshold, not much is happening. There's some spontaneous emission events. Then, as we increase the current, at some point we can see that as we increase the current, this G is increasing. So at threshold, this G becomes equal to 1 over tau photon. Okay. So basically, this is another way of just stating the threshold condition that gain is equal to loss, right? So remember, photon lifetime depends on the cavity loss we just saw, and this is some gain factor. So we're just saying gain equal to loss. This is a different way of writing what we wrote here, right? Same thing. Okay, so at threshold, basically, this quantity, so basically at threshold, this quantity becomes equal to 0, right? So now you can see that this quantity, the number of photons need not be 0 anymore, right? Just the product needs to be 0. So once G becomes equal to 1 over tau photon, so now this becomes finite, right? So as soon as we go to threshold, now we start generating photons in the cavity. Okay, so so from this threshold condition, we can actually find what is the threshold current here. Okay, because this is a practically measurable quantity, right? In the real world, I'll measure the current and power out. So I'll measure the current at which the power starts increasing, right? So the I threshold I can calculate from this condition. Right, so this again G, remember, was so G threshold is this constant Gn times the number of carriers at threshold minus this constant N0, which is basically the transparency carrier number, right? And I can calculate the number of carriers at threshold from here, right? So I'm saying as I increase the current just at threshold, right? So the photon number is 0 up to threshold, right? And the carrier number is given by this. So just at threshold, basically, you can see that the threshold current will give me the carrier number of carriers at threshold, right? So I can write this as I threshold tau c, right, minus n. Okay, and this is equal to 1 over tau photon, right? So if I just look at this equation here, everything is a constant, and I threshold is the unknown I want to find, right? Tau photon again depends on the cavity losses. So once I made my device, it depends on just the device constants. N naught also is a constant, tau c, gn, everything is a constant, right? So I can get an expression for the threshold current in terms of the device constants. So from there, you can see basically that I threshold okay, so you can see that the threshold current inversely proportional to the carrier lifetime, also inversely proportional to photon lifetime. Okay, so if I want a low threshold current, so right, which is what we want for an efficient device, the device. So basically, in some sense, we can say that the laser is off for I less than I threshold, and then it turns on for I more than I threshold, right? So if you want to turn it on at a low current, then basically I want large lifetimes. Right? I want large tau c and large tau photon. A higher lifetime for both the carriers and the photon gives me a more efficient device or lower threshold current. Okay. So one thing to note here is typically, like we saw this for the LEDs also, as we increase temperature, right? So let's say due to absorption in the defects or some heat is being generated in the device, and if the temperature of the device increases, right, that basically reduces this carrier lifetime. Okay, so the carriers now recombine faster, so the non-radiative rates go up due to, again, like the recombination in defects or some phonon-assisted recombinations. So basically, what happens is that, so you can see if the tau c goes down, so with increasing temperature, tau c goes down. This implies the threshold current goes up. Okay, so which is bad for my device. So typically, these lasers come with a temperature controller on the mount, okay, so that you control the temperature to a particular value, and because the device performance keeps degrading with increasing temperature. Okay. And typically, this dependence is actually exponential. So this I threshold typically goes as some I naught e to the T over T naught. Okay. So it scales exponentially with temperature. So it's quite bad. So temperature control is very important for lasers. We saw that it was important for LEDs also, but for lasers even more so. So this T naught here is about 70 Kelvin for the in-gas P devices that are used for the telecom devices. If you go to slightly shorter wavelengths, This goes up to about 120 Kelvin for AL-gas devices. So AL-gas devices, remember, they operate around 800 to 900 nanometers. So in terms of temperature performance, AL-gas are more stable because the T0 is higher. But yeah, so you can see that for telecom devices, temperature control is very important. This is not to say that we operate at 70 Kelvin, right? This T0, this constant is 70 Kelvin. But typically we operate somewhere near room temperature, but the point is that you need to control temperature. Because if you don't, if you just let the device to free run, then even just as the device operates, it generates heat due to some, again, these internal losses, etc. And then temperature starts increasing, and then the device starts degrading, and then this positive feedback loop, the device can fail. So temperature control is very important. Okay, so now, so that's the threshold current, right? Which again we can calculate. It just depends on device constant. So now, if we increase the current further, let's say we go beyond the threshold current, what happens? Right. So again, we come back to, let's say, this equation for the photons. So now, so we increase current beyond I threshold. Okay. So does that mean now that G can become more than 1 over tau photon, right? Naively, if we just say that this scales with the current, then G should now become more than tau photon, 1 over tau photon. So then, right, but that would mean that then this quantity becomes finite again. So then this n photon has to be 0. But of course, that physically doesn't make any sense, right? Beyond threshold, we actually expect the photon number to go up, right? Because now the device is on, simulated emission is now taking place. So you can see from this equation, the only way for it to happen is if this quantity remains 0. Okay, even for I greater than R. So above threshold, G remains equal to 1 over tau photon. Okay, so this is known as gain clamping. So this is what we sort of also discussed briefly last time with these gain profiles and loss profiles. Right? We said that so for these neighboring modes, also once you increase the gain, basically the gain gets clamped; it cannot exceed the loss. So that's what you can see from the equation here. Right? So for this to remain 0, and for n finite to become finite, this quantity has to remain 0. Okay? So this is known as gain clamping. So we can see that basically below threshold, this carrier concentration, the number of carriers, which gives me G, yeah, that increases with the current linearly up to the threshold, and then after threshold it just gets clamped, right? So what we are saying is that if I plot, for example, NC versus I. So first it increases linearly with current up to I threshold. Then it just gets clamped at the threshold value. Okay. Similarly, if you plot G, it increases up to G threshold, which is 1 over tau photon, and it just gets clamped. Okay, so yeah, so the gain gets clamped equal to the cavity loss, even for higher currents or above threshold. Okay, so then if you look at this other equation here, Yeah, so if you look at this equation now, right, left hand side is 0 in steady state. So now I have I over Q. I is now greater than I threshold. Okay, and then this number of carriers now is clamped, right? So I know for any current above I threshold, this NC is just NC threshold. Okay, and then this G also I know is just 1 over tau photon, right? For any current above threshold. So this term I can write like this. Okay. So NC threshold, remember, is a constant, right? It's this value. So you can see that this is an equation for basically the photon number in terms of the current. Everything else is constant, right? So this is what I'm looking for, right? I'm looking for the optical power versus the input current. So we can write this as okay, and then this Q NC threshold by tau C. So this is NC threshold. So Q NC is this I threshold. Okay, so above threshold, you can see that the photon number in the active region scales linearly with the current above threshold. Okay, so if I plot again, or maybe if I plot n photon on the same graph here, so n photon is 0 up to I threshold, and then it starts increasing linearly. Right? So this is n photon. Right? So up to threshold, the carrier concentration increases linearly, and the photon number is 0. Above threshold, the carrier concentration gets clamped, and the photon number increases. Okay, again, this was an approximation. We neglected the spontaneous emission lifetime, right? So actually, if you zoom in here, this is not actually 0, but there's a small slope here, right? Which is basically proportional to this, right? NC over tau R is the radiative rate. So there's some small slope here, which is the spontaneous emission, so the LED operation. But compared to this slope, that is almost 0. Okay, so that's all. Okay, so this n photon is basically the number of photons inside my device, right? So, right, so basically again, so I have my laser cavity, let's say, formed between these two mirrors. There's some active region here, so there are some photons generated here in the active region, right? So this is n photon, which is the number of photons here inside, right? But again, eventually I'm interested in what power is coming out of the device, right? So if I just had the simplest design where I just have cleaved facets on both sides, then the power can leak out from both sides, right? If I just want from one particular side, then I have to coat one of the sides with a high reflection coating to make that reflectivity close to 100%, so that it only comes out one side. But if you just take the simplest device where you just have three facets, then actually it can come out from both sides, right? And so if I look at the power coming out of any one side, that I can write as so factor of half first to say that I'm looking at only one side. So this half will change depending on again what device you have, right? So if you high reflection coated one of the facets, then this factor of half will go away. All the power will come out one side. And then the rate of photons leaking out from the device is basically the mirror loss, right? So basically the mirror loss then multiplied by the group velocity to make it per second, right? So this fraction, these are the number of photons now coming out per second, right? And photon is the number of photons in steady state inside my device. The rate at which photons are coming out per second is that multiplied by the mirror loss rate. And if I want to look at power in terms of watts, then I have to multiply by the photon energy. Right? So if I use this equation for the photon number, you can see that the optical power coming out basically looks like this. Right? Again, some constants here depending on what wavelength, which is again decided by the material, device parameters, photon lifetime, mirror loss, group velocity. So some constant times I minus I threshold. Right. So the Li curve or the Pi curve for a laser, you can see now is linear above threshold, but overall it's non-linear. Right? Unlike the LED, where it's basically a straight line starting from 0, but for the laser, it's sort of like that. Right? And so if I plot this on a log scale, so on the linear scale, it almost looks like this, like it's flat, 0 here, and then if you plot on the log scale, you can sort of see some effect of the spontaneous emission. So basically, there is some small slope here, and then suddenly at threshold, there's a huge jump. Okay, so below threshold, there is a small slope here, but it jumps by many orders of magnitude above threshold. Okay, so but if you plot on the linear scale, it almost looks so let's say numbers here we're talking about are like 10 to the minus 6 or something, and then suddenly you jump to 10 to the minus 3 and above. So Sometimes there is another factor included here, something called the internal quantum efficiency. But this is a different internal quantum efficiency as compared to what we had for the LED. Right? So for the LED, remember this was basically decided by the ratio of the radiative and the non-radiative lifetime. So basically, if the radiative lifetime was much shorter, then this internal quantum efficiency was higher because so this was basically the fraction of carriers which spontaneously recombine radiatively. Right? That was the internal quantum. For the laser, now we've gone into stimulated emission. So for stimulated emission, also one can define like an equivalent quantity where basically, let's say I have an incoming photon, and basically, so it stimulates a recombination of an electron hole pair. So now this recombination can again be radiative or non-radiative. So it can be radiative, which is what I want, but there could be some other parasitic processes where basically the stimulated emission does not happen, the stimulated recombination happens. Okay. So we can define an equivalent internal quantum efficiency for that. Okay, saying that the stimulated emission is not perfect 100%, but maybe slightly less. But turns out practically this is still very close to 1. So once you go into stimulated emission, at least 95% or more, with 95% or more efficiency, you generate a new photon. Okay. So sometimes you might see this additional factor here, but mostly we just assume that to be close to 1. Okay, so I can also, so this tau photon times Vg, right? So recall tau photon is 1 over Vg times the total cavity loss, which is the internal loss plus mirror loss. Right, so if I substitute this expression for tau photon here, I get this expression. Okay. So again, this is just some this is photon energy. So now you can see that the sort of determining factor for how efficient my device is, or basically how steep this slope is, right? So if this slope is steeper, then my device is more efficient, right? As compared to a shallow slope. Right, and the slope you can see is determined by this quantity, which is basically the ratio of the mirror loss to the total loss. Right, so the best case scenario is if the internal loss is much smaller than the mirror loss. Right, basically my total loss is just being decided by the mirrors. There is no loss internally. That's the best case scenario. And as soon as I have some internal losses, that makes this worse. So basically what you can see the best case scenario is we have a perfect cavity and only the mirrors are acting as losses. So just like LEDs, we can define some efficiencies here. Okay, so for example, we can define a slope efficiency, right, which is basically the slope here. Right, so dP by di. So this is some factor of depending on the photon energy and the electronic charge. So the power is proportional to the photon energy, right, and the current is proportional to electronic charge. So I keep those, and then have this eta d. Okay, so this is also just the h, if h means the band gap. Right, so this eta d is known as the slope efficiency, or sometimes a differential quantum efficiency. right? And that you can see is just this ratio of the mirror loss to the total loss, right? And if you include this efficiency of the internal quantum efficiency of this of the stimulated emission, you can include that also if you want. Okay, so again, typically, if you look at this differential quantum efficiency for sort of in-gas P lasers for telecom devices, it's about 50%. Okay, so this is something like the efficiency, the total efficiency that we had for the LED, right? And for the LED, we saw it was a product of the internal and external quantum efficiencies. And that value was like less than 1%. It was very small, right? But here you can see that it's going to go up to 50%. For AL-gas lasers, it can be even better. So this can go up to almost 80%. Okay, so you can see lasers are just way more efficient than LEDs. One can also define what is known as an external quantum efficiency. Okay, so that's basically the photon emission rate divided by the electron injection rate, right? So the photon emission rate is basically, so if P is the power coming out of one facet, then the total power coming out is 2P. So the photon emission rate is 2P by h nu divided by the electron injection rate is I over Q. Right, again, if I replace h nu by the band gap, so this just becomes okay, and if I use this expression for P in terms of I, you can see that this external quantum efficiency is basically just the differential quantum efficiency times this quantity here, depending on the current. Right, so it approaches the differential quantum efficiency for high currents. Right, so differential is basically giving you slope for a unit change in current, how much the power is changing. This is giving you sort of the total efficiency, right? Power divided by current. So you can see it's always smaller than this most slope efficiency. But if you go much above threshold, so if you go like way here, so this I threshold is very small compared to your operating current, then you can see that the slope efficiency is almost just right. This intercept doesn't matter too much. So this. Okay, and then finally there is something called as a total quantum efficiency. Or again, what is known as a wall plug efficiency. So this is like the total efficiency of the device, right? You plug it into a power source, what electrical power it's drawing versus what optical power it's emitting. Right, so this is the forward bias voltage V naught. So right, so basically h nu and q v naught are both sort of close to the band gap. Right, so the total efficiency is just sort of the external efficiency. up to a few percent. Okay. So again, for in-gas P, typical values for this total efficiency are, let's say, 20 to 30%. Right. So when you plug in the device, 20 to 30% of the power is drawing from your power, the electrical power source is being converted into optical energy. Right. Again, compare this with the LED, which was less than 1%. For all gas devices, this can be even higher, up to like 50%. Okay. And we already talked about this, that so if you look at the characteristics for increasing temperature, so what happens is that the threshold current increases and also the slope decreases. Okay, so these are for like 10 degrees Celsius, 20, 50, 100. Okay, so as the temperature increases, not only does the threshold current increase, but the slope efficiency also keeps falling down. So that's why temperature control is very important. So just to give you some scale here. Right, so this is the current in milliamp. This is the power watt coming out of one facet. Okay, so we'll stop here. So that finishes the DC characteristics, right? And next time we'll start the AC or the modulation characteristics. So if we send in a time varying current, how does the output optical power vary? And we find the modulation bandwidth for laser just like we did for LED. Any questions? Okay, and take care, everyone. Bye. Sorry, there's one question. Neglecting the spontaneous emission is neglecting optical noise. Yes. So you're right. Right. So spontaneous emission is basically like noise, right? So in other words, so for example, if you measure the power coming out of the laser as a function of time, right? For a particular set current. So let's say if I I operate the device at 10 degrees Celsius, set the temperature, set the input current to some 50 milliamp. Let's say I should get out some whatever 7 milliwatt here, right? So then basically the power should just be constant. So in our model, that's what we found, that this is exactly constant, right? But once you include spontaneous emission, turns out what happens is this is not perfectly constant, but there are fluctuations in the power. Okay, so there's some noise here, and so we'll see that basically the laser also will have some intensity noise, and also equivalently, if we look at, let's say the laser is operating a single frequency, so if you look at the electric field, it should just be a nice sinusoidal wave, right? But we'll see that there could be some phase jumps happening once in a while, just like intensity fluctuations. There are also phase fluctuations, right? And these intensity fluctuations and phase fluctuations will give me the line width of the laser. So the more the noise here, the broader the line width of the laser. And the ultimate limit will be given by the spontaneous emission. right? So spontaneous emission is acting like a noise source for my device, which will neglect it. But typically, like, so these fluctuations here, so if I look at the power fluctuations, so delta P by P is typically much less than 1% for lasers, for the semiconductor. So it's a very small value, but it's finite. So we'll discuss this maybe in the next class of what are these relevant noise mechanisms for the laser and how it affects the application that I want to use for, especially in this case, like telecommunication. Right. So this is known as the relative intensity noise origin of the laser is recorded. And this is phase noise. So spontaneous emission is the ultimate limit, right? So if you eliminate all other kinds of noise, so of course there could be some other physical mechanical sources of noise, like for example, the temperature is not perfectly set, it's fluctuating a little bit, right? Which you can imagine due to thermal expansion, the cavity length is changing slightly. Some other noise, like noise in the current, for example, the current source that you're supplying, of course, is also not perfect. There is some noise, right? So all these factors will give you some noise in the optical output. But let's say you eliminate all of that. Even then, finally, you will be left with spontaneous emission, which you cannot get rid of. It's like a fundamental quantum effect. And so the minimum noise that you can have will be, or the minimum laser line you can have will be determined by the spontaneous emission.